Welcome to the lecture on Geocoding of Maps, part of the Principles of Data Visualization lecture series. Now we'll begin today with the general discussion of spatiotemporal representation. So that's a mouthful. That's a lot to take in. Clearly, $25 or $50 set of words there. But it has fairly simple meaning. It's fairly straightforward as well. It basically just means, where am I in space at a particular time? So, spatiotemporal just means space and time. What is a representation? Visually, what does it look like at a particular place and a particular time? And what would normally be logical to go with that, if we're talking about space, often that'll lead to representations in maps, visual representations in maps. So, couple of different dynamics that are at work here. And particularly, this connects a lot to some of the aspects of narrative visualization, sort of the traditional PR oriented or strategic communications approach to creating a story. We answer who, what, where, when, and why. And this is a little bit of a takeoff of that to help us frame what we're working on here. So we'll start off with the first approach, where we combine when, so what time something happened and where was it, and that gives us what. So those are answering questions about an object at a given time and location. Okay, so that's sort of the definition of what. Then if we combine when and what, we have where. So those are answering questions about locations for objects at a given time. And notice that sort of what we've defined here is changed. And then the third type or iteration will be the combination of where and what, which will provide us when. So these help to answer questions for a particular time for a given object at a location. So again, that's answering when. So three different types of work we'll do here. Hopefully this simplifies those three types for us. Now let's talk a little bit more about data visualization with maps. So we all know maps are an intuitive way to visualize data in space and time. So as an example, here we have CrudeNet, which is basically short form for crude oil in barrels. What is the net balance for the top 10 countries in 2009? So basically, this is a measure of crude oil across the top countries in a particular year. So the mapping, so we see the map there on top, lets us engage data in a more robust way. So if we'd only presented the names of the countries in a bar chart down at the bottom there, we get some sense of the data, but we may not really get a full or as full of a sense of where is the geographic proximity or the spatial closeness or distance of these different countries from each other. And as we can tell here, you see the circles represented on the map. Some of these countries, probably a significant amount of them, form clusters in different, at least two of them, in different locations on the globe or different locations on the map, which could be meaningful. It might provide us with a little bit more information that we wouldn't have if we just had a simple listing with bar charts. Now, some different map types. As many of you guys are probably already aware and may use every single day, Google has several different variants of its maps. So the one you're most likely to be using is the road map. So it displays the default road map view. So we're zoomed out quite a ways here, but we can see the highway patterns there. We also have satellite maps. So what we're looking at here is a map, but it's a representation from a satellite photo. And often we can zoom in and get very accurate up to probably the residential home on a street. And we could probably get a pretty decent image there without getting too much more detailed than some of the features on that home. We also can have a hybrid, so we can utilize our satellite map and overlay the highways on top of it or the streets on top of it to give us a sense of how do these locations fit within the different terrain or trees, parks, etc. And then finally, a terrain map displays a physical map based on terrain information. So is there a building, grass, dirt, etc.? It gives us just a little bit more information on what's going on versus the pure map or the pure satellite view. Now, there are lots of different ways of representing time. We've predominantly been discussing maps and representing things in space. Now we're going to talk about representing different representations in time. So there are two major time primitives, what are called time primitives. Another way of stating that would just be types of time or types of ways or ways we could measure time. So the first one are points in time. So we have, it's 5:30, 6:05, and 7:10. So those are different points in time on pick any month. Now, as it's not necessarily in contrast, but a different approach of representing time. The second approach would be with a time interval. So a time interval might ask or present how much time has passed. So it might be 8 hours, it might be 24-hour cycles, but they're intervals, basically segments of time put together with a from and a to time and date stamp. And then there are three types of time structures. So the first one is ordered time. So with ordered time, time can be represented in a linear way, basically the arrow of time. So this is probably easiest to think about if I have a data visualization with an x-axis across the bottom, and perhaps I'm just representing quarterly reporting. I might have my quarter, that is my most historic quarter, represented on the left of the x-axis, and then repeating quarters up until my most recent quarter represented on the far right of the x-axis. So an arrow of time. Or cyclical. So with cyclical time, I have a 24-hour clock that is counting, but I'm basically counting those 24-hour cycles. So the cyclical is a second way that we can order time. I can also have what's called branching time, so some alternate paths that someone could go with different time frames. And then I can have the third, or what are known as multiple perspectives. And a good example of that is time zones. So if we ask what time is it, that might depend on where you are in the world. Your perspective might be different. So first, let's take a look at points in time. So here we have Menard's famous visualization of Napoleon's march, we should say fateful march, to Moscow. Now, the main thing that we want to highlight here is that our flow map, which Menard is famous for, these different battles or thicknesses of the line, as well as geographies of a particular town where a battle might have been fought, occurs at a particular point in time. So these are laid out with particular dates and times as Napoleon moves into Moscow and then retreats from Moscow. So each of those particular points in time, time and date stamps, provide us with a point in time. Now, we also suggested that we can have time intervals. And let's talk a little bit about what another example of a time interval. We had given the 24-hour cycle as a time interval. But how? Let's examine these data visualizations a little bit closer. So you'll notice the scale first. So if you look in either of the images, you'll see in the bottom left-hand corner a scale that is basically 0, 5, and 10. It's a minute scale, and it's that 10 minutes is represented with our alternating colors or rings here. So what you see is at the very center, let's take a look at the visualization on Piccadilly Circus. You'll notice that at the center, it's all white. We have basically a 10-minute interval from the center point until we reach the edge of the first gray ring. It'll take 10 minutes to get across the first gray ring. And then when we get to the edge of that ring, it'll take us another 10 minutes to get through the white ring, another 10 minutes to get through the second gray ring, another 10 minutes to get through the third white ring, another 10 minutes to get through the third gray ring, etc. So what you're looking at is basically a map of time intervals. Now, how can this be useful? Well, the way that this is useful is what we see here is an overlay of a particular train station, subway station, called Piccadilly Circus in the London Underground or London tube stops. So what you can do is from Piccadilly Circus, which that train station is in the center of this map, you can follow the particular train map, that particular train line, and figure out how long is it going to take me to get to the location that I'm interested in. And it's laid out with this time interval scale as a background, so it's easy for the user to basically count how much time it will take. And then we see the same thing in the right-hand visualization with the Highgate train stop. So if we get on that black line, we can follow it. We will probably spend somewhere in excess of 15 minutes getting wherever we're going, because it takes us 10 minutes to get across the white circle in the center, at least 5 minutes to get across half of that first gray ring, and then I can pick up another train line represented by the different colors, or I can stay on that same black train line to reach a destination. So this is a good overview of how a time interval can be represented visually in a data visualization. Now, where does all this come from? So originally, this data visualization was created by Henry Charles Beck. It's a very famous data visualization map, and it's considered one of the best maps created of all time. And my question to you guys is, what's the underlying basis of this? And we've discussed this before. This is the second time you guys have seen this map. So what's the underlying basis of this map? As many of you guys may remember, that this map is laid out for the user. So their utility is basically to know, I get on one train station, how many train stations until I get off, and that is the utility in this map. And there are some large geographical features that work here. We do see the river, and we can know, hey, are we north or south of the river? But predominantly, we're not focused on the geographic proximity or the accuracy of the geography in this map. We're just interested in the utility of moving from one train station to the next. And you'll notice that it would be highly unlikely that the geography would actually be laid out the way this map is represented. Now, animation versus multiple view. So with animated visualization, the audience focuses on changes to data encoding. So basically what we may be looking at is data is encoded in one way. It may change to encoding in a second type. The audience looks for particular events. Their focus has changed in animation. Instead of comparing two shaped objects, they're looking for events or patterns that emerge in the motion. And with animation visualization, we disengage that spatial layout to a large extent. We're really just looking at the action, the flow, the process, the direction of the data. Now this is quite a bit different than our multi-view data visualization, basically small multiples, trellis charts, that is more focused on spatial representations and patterns. So we're basically doing comparisons between visualizations based on the space that is used or isn't used, and how those compare to each other. And it's a lot less focused on events and or time. Now, to provide a great example of some animated data visualization, we have here the dynamics of vehicle motion. It's provided by Pedro Cruz. And basically, it gives us an animated visualization of traffic patterns in Lisbon, Portugal. Now this next data visualization is an example of hurricane tracking. So this one happens to be provided by the New York Times. But whenever there is a hurricane, often the National Weather Service or NOAA will go out and fly over a particular hurricane location and drop a bunch of very lightweight tracking devices that'll get swept up into the winds of the hurricane. And what that allows organizations that track hurricanes to do is get a geolocation on where is the center of the hurricane. And what we see represented here is basically a tracking pattern at different points in time. So we see, if we start down at the bottom, this is Thursday at 1 a.m. Where the hurricane was. We see sort of 3 different intervals in between, and then where will it be Friday at 1 a.m. And then we see 3 more intervals in between, and where will it be Saturday at 1 a.m. And so in what we're looking at here, this is the path of Hurricane Patricia. It was one of the most powerful hurricanes in world history that basically hit central Mexico on the Pacific side. And so it gives you kind of a sense of the path, as well as some variability of the area that might be impacted by hurricane force winds. We can also look at flight patterns. So this is a data visualization provided by Aaron Koblin that demonstrates flight paths in the United States. A couple things to notice about the encoding here. So we have different color encoding for different types of flight paths. You'll see the number of planes represented on the bottom left-hand corner. And then on the right-hand side, you will see in Eastern Standard Time, basically a time and date stamp clock that cycles throughout a particular day or a 24-hour cycle. Now here's an example of the Menard flow map of Napoleon's march into Moscow and back, but it's represented in 3 dimensions. So this is the Menard map in the 3rd dimension. This was created by Menno Jan Crack, and you can see the visualization on the right-hand side. Basically, there's a starting point. The months are the depth dimension. So when we start this, or when the march begins, it's probably down at the bottom here. And the march proceeds sort of up the elevation, which would be equivalent to the across, left to right, that is in the 2D version. And it's marked in each particular month, so it lets us know sort of the march across each month. There's a particular node that's highlighted in time for each of these months. We also have slightly different highlight or color code in the spheres, the 3D spheres, representing month and location when you get to Moscow. And that's represented sort of on this top level or near the top level plane. So the army gets to, or Napoleon gets to Moscow and then begins to march out. So it's kind of a unique representation, a little bit different than the 2D. Yes, there's plenty of debate on does it work any better than the 2D version, and I might be one of the voices that says probably not. But I do think it's an interesting way to look at mapping, basically creating spatiotemporal maps or visualization in a 3D way. Now, the next spatiotemporal visualization we want to look at is a project that was created by Deb Roy and Rupal Patel. It's presented by Deb Roy, and basically is called Housefly. To give you a little bit of overview, the data visualization that you're looking at is a screen capture from the video that you're about to watch, and what's highlighted in the green pass are Deb Roy's children moving throughout an apartment, as well as the red lines are the movement patterns of the caregiver. And so from these pass, a number of things can be inferred. We'll roll the video, let you guys take a look at it, and then we'll return for some analysis.
Imagine if you could record your life. Everything you said, everything you did, available in a perfect memory store at your fingertips. So you could go back and find memorable moments and relive them, or sift through traces of time and discover patterns in your own life that previously had gone undiscovered. Well, that's exactly the journey that my family began 5.5 years ago. This is my wife and collaborator, Rupal, and on this day, at this moment, we walked into the house with our first child, our beautiful baby boy. And we walked into a house with a very special home video recording system.
Ready? 1 second. Okay.
This moment and thousands of other moments special for us were captured in our home, because in every room in the house, if you looked up, you'd see a camera and a microphone. And if you look down, you'd get this bird's eye view of the room. Here's our living room, the baby bedroom, kitchen, dining room, and the rest of the house. And all of these fed into a disk array that was designed for continuous capture. So here we are flying through a day in our home as we move from sunlit morning through incandescent evening, and finally lights out for the day. Over the course of 3 years, we recorded 8 to 10 hours a day, amassing roughly 250,000 hours of multi-track audio and video. So you're looking at a piece of what is by far the largest home video collection ever made. I think that's clear. And what this data represents for our family at a personal level, the impact has already been immense, and we're still learning its value. Countless moments of unsolicited, natural moments, not posed moments, are captured there, and we're starting to learn how to discover them and find them. But there's also a scientific reason that drove this project, which was to use this kind of natural longitudinal data to understand the process of how a child learns language, that child being my son. And so with many privacy provisions put in place to protect everyone who's recorded in the data, we made elements of the data available to my trusted research team at MIT so we could start teasing apart patterns in this massive data set, trying to understand the influence of social environments on language acquisition. So we're looking here at one of the first things we started to do. This is my wife and I cooking breakfast in the kitchen. And as we move through space and through time, a very everyday pattern of life in the kitchen, in order to convert this opaque 90,000 hours of video into something we can start to see, we use motion analysis to pull out, as we move through space and through time, what we call space-time worms. And this has become a part of our toolkit for being able to look and see where the activities are in the data, and with it, trace the patterns of, in particular, where my son moved throughout the home, so that we could focus our transcription efforts, all the speech environment around my son, all the words that he heard from myself, my wife, our nanny, and over time the words he began to produce. So with that technology and that data and the ability to, with machine assistance, transcribe speech, we've now transcribed well over 7 million words of our home transcripts. And with that, let me take you now for a first tour into the data. So you've all, I'm sure, seen time-lapse videos where a flower will blossom as you accelerate time. I'd like you to now experience the blossoming of a speech form. My son, soon after his first birthday, would say gaga to mean water. And over the course of the next half year, he slowly learned to approximate the proper adult form, water. So we're going to cruise through half a year in about 40 seconds. No video here, so you can focus on the sound, the acoustics of a new kind of trajectory. Gaga to water.
Gaga, 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 gaga,
He sure nailed it, didn't he? So he didn't just learn water. Over the course of the 24 months, the first 2 years that we really focused on, this is a map of every word he learned in chronological order. And because we have full transcripts, we've identified each of the 503 words that he learned to produce by his second birthday. He was an early talker. And so we started to analyze why. Why were certain words born before others? This is one of the first results that came out of our study a little over a year ago that really surprised us. The way to interpret this apparently simple graph is on the vertical is an indication of how complex caregiver utterances are based on the length of utterances. And the vertical axis is time. And all of the data we aligned based on the following idea. Every time my son would learn a word, we would trace back and look at all of the language he heard that contained that word, and we would plot the relative length of the utterances. And what we found was this curious phenomena that caregiver speech would systematically dip to a minimum, making language as simple as possible, and then slowly ascend back up in complexity. And the amazing thing was that that bounce, that dip, lined up almost precisely with when each word was born, word after word, systematically. So it appears that all three primary caregivers, myself, my wife, and our nanny, were systematically, and I would think subconsciously, restructuring our language to meet him at the moment of the birth of a word and bring him gently into more complex language. And the implications of this, there are many, but one I just want to point out is that there must be amazing feedback loops. It's not, of course, my son is learning from his linguistic environment, but the environment is learning from him. That environment, people, are in these tight feedback loops and creating a kind of scaffolding that has not been noticed until now. But that's looking at the speech context. What about the visual context? We're now looking at, think of this as a dollhouse cutaway of our house. We've taken those circular fisheye lens cameras and we've done some optical correction, and then we can bring it into three-dimensional life. So welcome to my home. This is a moment, one moment captured across multiple cameras. The reason we did this is to create the ultimate memory machine where you can go back and interactively fly around and then breathe video life into this system. What I'm going to do is give you an accelerated view of 30 minutes, again, of just life in the living room. That's me and my son on the floor, and there's video analytics that are tracking our movements. My son is leaving red ink, I'm leaving green ink. We're now on the couch looking out through the window at cars passing by, and finally my son playing in a walking toy by himself. Now we freeze the action, 30 minutes. We turn time into the vertical axis, and we open up for a view of these interaction traces we've just left behind. And we see these amazing structures. These little knots of two colors of thread we call social hotspots. The spiral thread we call a solo hotspot. And we think that these affect the way language is learned. What we'd like to do is start understanding the interaction between these patterns and the language that my son is exposed to see if we can predict how the structure of when words are heard affects when they're learned. So in other words, the relationship between words and what they're about in the world. So here's how we're approaching this. In this video, again, my son is being traced out. He's leaving red ink behind, and there's our nanny by the door.
You want water? All right.
She offers water, and off go the two worms over to the kitchen to get water. And what we've done is use the word water to tag that moment, that bit of activity. And now we take the power of data and take every time my son ever heard the word water and the context he saw it in, and we use it to penetrate through the video and find every activity trace that co-occurred with the instance of water. And what this data leaves in its wake is a landscape. We call these wordscapes. This is the wordscape for the word water. And you can see most of the action is in the kitchen. That's where those big peaks are over to the left. And just for contrast, we can do this with any word. We can take the word bye, as in goodbye, and we're now zoomed in over the entrance to the house, and we look and we find, as you'd expect, a contrast in the landscape where the word bye occurs much more in a structured way. So we're using these structures to start predicting the order of language acquisition, and that's sort of ongoing work now. In my lab, which we're peering into now at MIT, this is at the Media Lab, this has become my favorite way of videographing just about any space. Three of the key people in this project, Philip DeCamp, Ronnie Kubat, and Brandon Roy, are pictured here. Philip has been a close collaborator on all the visualizations you're seeing. And Michael Fleischman was another PhD student in my lab who worked with me on this home video analysis. And he made the following observation, that just the way that we're analyzing how language connects to events which provide common ground for language, that same idea we can take out of your home, Deb, and we can apply it to the world of public media. And so our effort took an unexpected turn. Think of mass media as providing common ground. And you have the recipe for taking this idea to a whole new place. We've started analyzing television content using the same principles, analyzing event structure of a TV signal, episodes of shows, commercials, all of the components that make up the event structure. And we're now, with satellite dishes, pulling in and analyzing a good part of all the TV being watched in the United States. And you don't have to now go and instrument living rooms with microphones to get people's conversations. You just tune into publicly available social media feeds. So we're pulling in about 3 billion comments a month. And then the magic happens. You have the event structure, the common ground that the words are about coming out of the television feeds. You've got the conversations that are about those topics. And through semantic analysis, and this is actually real data you're looking at from our data, our processing. Each yellow line is showing a link being made between a comment in the wild and a piece of event structure coming out of the television signal. And the same idea now can be built up, and we get this wordscape, except now words are not assembled in my living room. Instead, the context, the common ground, the activities are the content on television that's driving the conversations. And so what we're seeing here, these skyscrapers now, are commentary that are linked to content on television. Same concept, but looking at communication dynamics in a different, very different sphere. So fundamentally, rather than, for example, measuring content based on how many people are watching, this gives us the basic data for looking at engagement properties of content. And just like we can look at feedback cycles and dynamics in a family, we can now open up the same concepts and look at much larger groups of people. This is a subset of data from our database, just 50,000 out of several million, and the social graph that connects them through publicly available sources. And if you put them on one plane, a second plane is where the content lives. So we have the programs and the sporting events and the commercials and all of the link structures that tie them together make a content graph. And then the important third dimension. Each of the links that you're seeing rendered here is an actual connection made between something someone said and a piece of content. And there are, again, now tens of millions of these links that give us a connective tissue of social graphs and how they relate to content. And we can now start to probe the structure in interesting ways. So if we, for example, trace the path of one piece of content that drives someone to comment on it, and then we follow where that comment goes and look at the entire social graph that becomes activated, and then trace back to see the relationship between that social graph and content, very interesting structure becomes visible. We call this a co-viewing clique, a virtual living room, if you will. And there are fascinating dynamics at play. It's not one way. A piece of content, an event, causes someone to talk. They talk to other people. That drives tune-in behavior back into mass media. And you have these cycles that drive the overall behavior. Another example, very different. Another actual person in our database, and we're finding at least hundreds, if not thousands of these. We've given this person a name. This is a pro-amateur or pro-am media critic who has this high fan-out rate. A lot of people are following this person, very influential, and they have a propensity to talk about what's on TV. So this person is a key link in connecting mass media and social media together. One last example from this data. Sometimes it's actually the piece of content that is special. So if we go and look at this piece of content, President Obama's State of the Union address from just a few weeks ago, and look at what we find in the same data set at the same scale, the engagement properties of this piece of content are truly remarkable. A nation exploding in conversation in real time in response to what's on the broadcast. And of course, through all of these lines are flowing unstructured language. We can X-ray and get a real-time pulse of a nation, real-time sense of the social reactions and the different circuits in the social graph being activated by content. So to summarize, the idea is this. As our world becomes increasingly instrumented and we have the capabilities to collect and connect the dots between what people are saying and the context they're saying it in, what's emerging is an ability to see new social structures and dynamics that have previously not been seen. It's like building a microscope or a telescope and revealing new structures about our own behavior around communication. And I think the implications here are profound, whether it's for science, for commerce, for government, but perhaps most of all for us as individuals. And so just to return to my son, when I was preparing this talk, he was looking over my shoulder, and I showed him the clips I was going to show to you today, and I asked him for permission, granted. And then I went on to reflect, isn't it amazing? This entire database, all these recordings, I'm going to hand up to you and to your sister, who arrived 2 years later. And you guys are going to be able to go back and re-experience moments that you could never with your biological memory possibly remember the way you can now. And he was quiet for a moment, and I thought, what am I thinking? He's 5 years old. He's not going to understand this. And just as I was having that thought, he looked up at me and said, so that when I grow up, I can show this to my kids? And I thought, wow, this is powerful stuff. So I want to leave you with one last memorable moment from our family. This is the first time our son took more than 2 steps at once, captured on film. And I really want you to focus on something as I take you through. It's a cluttered environment. It's natural life. My mother's in the kitchen cooking, and of all places in the hallway, I realize he's about to do it, about to take more than 2 steps. And so you hear me encouraging him, realizing what's happening, and then the magic happens. Listen very carefully. About 3 steps in, he realizes something magic is happening. And the most amazing feedback loop of all kicks in, and he takes a breath in, and he whispers, wow. And instinctively, I echo back the same. And so let's fly back in time to that memorable moment. Hey, come here. Can you do it? Oh boy, can you do it? Now he's walking. Thank you.
Now, some of the results of this particular video provide us with geospatial stacks of words, if you will. And if you look down on the bottom of this visualization, we'll see those same red and green paths that we were talking about that basically have passed through the apartment. But the thing that's been added here are the words that are said at particular geolocated positions in the apartment. And you see those sort of streaming upwards from the bottom view up to the top view there. And then what you see in the top view is basically a map that gives us the relative stacks of words, or where all of the words were said and what was the quantity of those particular terms being said. And in this particular case, this is the geolocation in the apartment of all the locations where Deb Roy's son said water. And you can see from looking at this particular map, we can see the mounds of where water was said, and those happen to be where the kitchen is, as well as the water closet or restroom. So we can see those laid out there. And of course, there are other locations throughout the apartment where the term water was used, just not as many times in aggregate. And so this gives us a very nice sort of spatial temporal overlay of how are words used in a sort of human dynamic and human context of real life. Now moving on, this is a data visualization, again, visualizing mobility, basically how people move throughout a city. We can see color-coded in different colors here, how folks in their vehicles proceed to a particular path, like a highway. When they join that path, if they join with lots of other citizens, that path is represented in a much larger line, similar to a flow map. And it also gives us a sense of where are folks coming from that end up perhaps as traffic on a particular highway. So we see that representation here for Milan, Italy. And then our last example that we'll look at here is basically uses social media, basically tweets from Twitter as the context for data visualization, particularly across a number of events. And one of the particular events here is that's represented is a significant earthquake in Japan. You'll notice up at the top we define sort of the layout. In this particular layout, we're looking at the longitude because it gives us a better sense of that location on the Earth. And then you can see color-coded either positive, neutral, or negative tweets. And what we see here represented is the paths of those tweets from particular geographies. So we might have, say down at the bottom, we have a number of tweets about the Japanese earthquake, all coming from Europe. And we can see there the sentiment on those is for the most part neutral. We have one, I think, that is negative, but in general we could get a sense of what is the European view of the Japanese earthquake there. Then we might move over on the top right hand of the globe. We see the tweets coming from different locations in Japan for this particular earthquake, sort of back and forth, predominantly neutral, but certainly connecting to some others there. And then we see other locations, looks like Australia, Taiwan, those tweets tend to be a little bit more negative, but maybe some more positive ones from the Philippines and Thailand. So you get the idea here where what we see represented is a particular event, a major event, and what all the tweet traffic looks like regarding that particular event. Now we'll take a look at an application called Social Media Whisper. This particular application compiles a set of social media tweets from Twitter and allows analysis of those, particularly the relationship of various tweets with events, transposed across the globe, so with a visualization of the globe. And so if we start up at the top here, when you watch the video, I want you to look for a couple of things. First, the view can be changed on the map. So you'll notice that in the center of the circle here is actually a map of the globe. And there's an equal area layout as well as a longitude layout. So there'll be some differences that you can see there. The way that this application is organized, in the center, you'll have whatever a particular event is or particular topic of focus will be at the center. And then different tweets will emerge. They'll have a particular sentiment. They can be positive, neutral, or negative. And then there can also be tweets that are emerging, sort of retweeting on the same topic or event, and you see those from different locations around the globe that will be connecting to the tweets in that particular area. And then as the video goes through, you'll see a couple of different encoding aspects. You'll see a tooltip, so you're able to hover on a particular tweet as well as that particular user. And then down at the bottom, there'll be some navigation overview so you can review or analyze in an exploratory way the temporal or time-based timeline for the tweets. So I think it's pretty interesting data visualization that combines both the data visualization aspects as well as geocoding and kind of integrates all those together. So I hope that you enjoy it. Now let's talk about mapping locations on Earth. So in order to make sense of the Earth and different locations, to give us a perspective on where different things are, a geographic system of coordinates was developed. Basically, latitude and longitude is the way that it's a common way that we've all agreed, or all the countries around the world, all the peoples around the world have agreed to measure or determine where someone might be or where a location might be on Earth. So the first part of the system is longitude. So longitude measures east and west, basically directions east and west. And then latitude is the second part of the system that measures locations north and south. So with these two measurements, it basically creates a grid. And of course, it's a grid placed on top of a sphere. And it helps us precisely define positions on Earth. So we're providing a video from Andy Jensen that walks you through an animated overview of how the latitude and longitude system works. And then we will pick up and discuss some examples, some real-world examples on how we apply this system.
Earth, our home in the vast universe. The Earth's circumference is nearly 25,000 miles from start to finish. There are so many places on the Earth. How is it possible to precisely locate just one of them? For instance, what if I wanted to tell a friend the exact location of the Coronado Bridge in San Diego? It would be hard to describe, but give him the coordinates of the bridge and he should be able to find it quite easily. To find precise locations, parallels of latitude and meridians of longitude form an invisible grid over the Earth. Latitude. Lines of latitude, also known as parallels, circle the globe from east to west. These lines are all the same distance apart, about 69 miles. Each degree of latitude is separated into smaller pieces called minutes. There are 60 minutes in 1 degree. Similarly, each minute is divided into 60 seconds. The equator lies at 0 degrees, halfway in between the North and South poles. There are several other unique lines of latitude. The Tropic of Cancer lies at 23.5 degrees north, and the Tropic of Capricorn lies at 23.5 degrees south. The part of the Earth that lies between these lines is called the tropics. It's known for its hot temperatures, heavy rainfall, and dense jungle. The Arctic Circle lies at 66.5 degrees north, and the Antarctic Circle lies at 66.5 degrees south. The area of the Earth between these parallels and the tropics is characterized by 4 distinct seasons. Longitude. The lines that run north and south are called meridians of longitude. These lines are measured the same way as parallels of latitude using degrees, minutes, and seconds. However, unlike latitude, lines of longitude are not equidistant from each other. Meridians intersect at the north and south pole. 0 degrees longitude is called the prime meridian. It passes through the Royal Greenwich Observatory in Greenwich, England. Using latitude and longitude, the precise location of San Diego can be written as 32 degrees, 42 minutes, 54 seconds north latitude, 117 degrees, 9 minutes, 25 seconds west longitude. Parallels of latitude and meridians of longitude form an invisible grid over the Earth. This grid is measured in degrees, minutes, and seconds, and it allows us to pinpoint exact locations anywhere on the face of the Earth.
So let's take a look at the center of the system. So this latitude and longitude system, this grid, was developed at the Royal Observatory in Greenwich. And this particular location, for reference, it's basically pretty close to London, England. And what we have in front of us here, you can see the map there. We've highlighted this particular location. You can see the River Thames there. You can imagine where London is. So I know that England is pretty good distance north from the equator. It's not quite so far north that it's at the North Pole, but it's north. And so now we'll specifically look at our system and talk through, okay, what does it mean to be in the Royal Observatory in Greenwich and near London? So let's take a look at either the Google or the Yahoo definition of latitude and longitude. There are several different open source systems to define latitude and longitude. We've given you 3 popular ones in each of these examples: Google, Yahoo, and one at Texas A&M University. So let's take a look at the latitude as described from the Google system. So we notice that we're at 51 degrees latitude. And as you may recall, that's going to give us some positioning from on the north and south. And the 51 degrees tells us that we're a pretty good distance from the equator. So the equator is that center line on the north-south direction of the Earth. And 51 degrees is pretty far north, which is what we would expect if we're near London, England. Now the longitude on this system is quite interesting. So you may remember that the longitude measures sort of our east-west direction. And notice that this one's fairly peculiar. It's at 0 degrees. Notice that our system here is expressed in degrees, minutes, and seconds. And as the video described, minutes are a fraction of degrees, as are seconds. Now this one's peculiar in that it's 0 degrees, and the reason for that, the explanation for why it's at 0 degrees, is that this particular laboratory came up with the system. And so they put themselves sort of at the center of the system, and they start with 0 degrees, basically sort of a tip of the hat to this particular Royal Observatory that says you're at the center of the system from east-west direction. And that's why they received the 0 degrees. Now let's take a look at something that may be a little bit closer for some of us. Let's take a look at Richardson, Texas. So if we look on the left-hand side of the screen here, that's a map of Richardson, Texas. Of course, Richardson is just north of Dallas, Texas. And we'll take a look at the Google system again and notice that our latitude measurement is at 32 degrees. Now, let's notice a couple things. So that number of degrees, 32, is quite a bit less than what we were looking at in the 50s for London, England. And that makes sense in that we're a lot closer here in Richardson. We're a lot closer to the equator than folks in London, England. They're a considerable distance further away from the equator. And so you can tell from the measurement here of 32 degrees that puts us a lot closer to the equator versus the 50-something degrees that we found in the previous example for the observatory near London, England. So hopefully that gives you a little bit of perspective on, yes, okay, this is working north and south. Richardson is a considerable distance south from London, England. And so it makes sense that we have a smaller measurement of 32 degrees latitude versus the 50s. Now let's take a look at the longitude measurement. So the longitude measurement here measures east and west, as was described in the video and as we talked about before. Now, if you recall, the Royal Observatory was at the center of the system, and we're at negative 96 degrees here. And remember, longitude works on east-west. So let's describe sort of what's going on here. So the Earth rotates in a particular direction. So, and you can think about the time zones that move across the Earth. It becomes the next day in London, many hours before the next day in New York or in Richardson, Texas. Now, in London or at the observatory, they're at 0 degrees of longitude, and we're at negative 96 degrees. Now, why negative, and why negative 96 degrees? So if we stand in the Royal Observatory and then we move to the location of Richardson, so we're moving west, but that's actually in a negative direction or against the spinning of the Earth. And that's why it gets its negative notation there. So it's negative 96 degrees. So we're a pretty good distance away from London. And we're in a negative direction because we're moving against the direction that the Earth spins. And that's how we get the negative numbers there. Now let's take a look at Berlin. So Berlin will give us a little bit different perspective, being on the east side of London. So Berlin would be, we would have to move east to get to Berlin from London. And let's take a look at its coordinates. So in the Google system, we see its latitude is defined at 52 degrees, 30 minutes, and 55 seconds. That would make sense because Berlin is also quite a distance north from the equator, just like London, England. So that makes sense to us. And then if we look at our longitude, we're actually moving to the east of London, England. And notice that that's a positive number. So that's a positive measurement of 13 degrees. And what that notation is we're actually moving with the direction of the Earth spinning on its axis. So we get a positive number of 13, meaning that we're east of Greenwich, or the Royal Observatory in London, and we're at 13 degrees. So hopefully with those three examples, it gives you different perspectives about where these locations are in reference to each other, and some specific measurements in the geocoding system to give you a feel for how does that system work north to south as well as east to west. Now there are cases where we may find particular locations in our applications have no geocoding address. Now that doesn't mean they don't have a position on the Earth, of course. Of course that they do, but it may be the case that the particular software that we're using or a particular system does not have this particular location in its index. And so what we have listed here is a number of locations that we know exist that we would like to geocode. Our particular system wasn't able to geocode them because these locations weren't in the index. And one of the things you'll notice about many of these locations are these locations are in North America, and notice that many of them are Indian reservations. So we'll see several different Indian reservations. In the news recently has been the Standing Rock Sioux tribe of North and South Dakota. More recently, that's just come onto the map in sort of the popular media. But many of these locations are Indian reservations. And what's likely going on here, the reason why these didn't geocode, is that these particular locations aren't in the state or local taxation systems, which are often closely associated with the issuing of geocoordinates or the indexing of geocoordinates. And specifically, many of these particular Indian reservations are seen as nations within a nation. So if you can imagine, these are something that's probably along the lines of a county. In some cases, it could be as small as a neighborhood, but it's actually legally a nation that exists within the United States and North America. So we have provided some examples of these for you guys in your assignment. And the reason why we've done that is this is a very sort of real-world exercise where you have to look up and find particular geocoordinates that may be close to this location that you can utilize to complete your data set. Now, I also wanted to give you guys some exposure to a system called ArcGIS that's provided by the Esri Software Corporation. So Esri is the industry standard for geospatial information systems. They started doing this work back in the 60s. They've been around a long time, and ArcGIS is really the standard by which all geographic information systems are measured by. So we've provided a couple of different videos for you. The first one is about Esri as a company and ArcGIS. And then the second one is using Esri and ArcGIS in a business context for a particular retailer.
Even the birds?
Some birds fly south in the winter.
Do they go where the penguins live?
I don't go that far. Penguins live really far south, where it's freezing cold.
Where's that?
Let's take a look. Here's a map of the South Pole where penguins live.
Let me see.
Look, someone's tracked their migration on the map.
Temperature is minus 18 degrees centigrade today in the Ross Sea of Antarctica. The Adélie penguins have returned from their nearly 13,000 kilometer journey, where they fed on krill, squid, and silverfish. They venture north during winter because they need light and open water to forage in the ocean.
In addition to our main menu, we have some specials tonight. Fresh calamari flown in from Santa Cruz, filet mignon from the Blacktail Mountains of Dillon, Montana, fresh king crab from Bristol Bay, Alaska, and fresh kiwi salad from New Zealand.
February 9, 2011, 3 a.m. This is the Spirit of Enderby departing from Port of Bluff, New Zealand. Current position, 47.1 degrees south, 168.2 degrees east, steering 174, making 10.8 knots en route to Ross Island. We have landed at Auckland Islands, and while walking through the Rattle Forest, we stumbled across seals resting on the grass. We have deployed the first Argo float at 51.4 degrees south, 165.1 degrees east, and it is now sending data to our satellite. There is a lot of ice around Cape Adare, so we have to make our way around that to get to our next destination, Franklin Island. We should spot a large rookery of penguins there.
This is a great trail.
Yeah, fast and beautiful.
Let's follow the trail on the left. It takes us to a great view of the coastline. Whoa!
透過公共交通、人口統計以及人口數字呢3層，我哋可以揾出房屋需求最高嘅地點，並響投資新嘅多用途發展計劃同埋選擇地點嘅時候加以配合。呢一區提供戶外活動，但依然接近市區中心。
That was a great ride. Now how about the Appalachian Trail for our next trip? Cool. I'm in.
Sarah, this is Weiser State Forest Station. Can you provide the GPS plots for the impacted areas from the fire last year and the reforestation zones? Over.
Copy that. I'm near the first reforestation area now. Then we'll give you GPS coordinates of the area, outline, and some current photos for the map. Over.
This is where we saw the deer. It's about a mile up and we reach Eagle's Nest Shelter, where we can spend the night.
Awesome. Let's go.
My name is Jillian Elder. I'm the director of our Enterprise Location Intelligence team at Walgreens. Our Enterprise Location Intelligence group is well placed right in our corporate strategy organization. What this means is that we're well positioned in order to service a bunch of the divisions throughout the company. So we end up partnering with divisions across the entire company to improve upon the information that's going into their decisions.
Understanding our customers, where they live, where they work, why they're shopping us is the core of what we do, and that's in many ways a spatial question. Our work and our spatial analysis and our mapping technology is centered around serving customers.
Walgreens has started an initiative to offer flu shots at nearly every location. With a network of 8,000 stores, we really have the ability to identify sales trends of products that are relating to flu. And with that, a flu index was created.
Now, the way we get this data is we use our prescriptions for antiviral medications. And that, for us, is our best indicator of flu activity, because generally speaking, when someone has a positive flu test, they're getting prescribed an antiviral to help treat it.
When we combine that in with our mapping applications, we were able to, before the CDC could report on it, understand where flu was happening throughout the country.
It was very important for us to have a simple mapping platform that would illustrate what we were showing in the flu index each week. What the CDC does is their data is reported on a 2-week lag, whereas inside of a week we're able to turn around data. So I think that, that really helped us in terms of the credibility of the flu index, because ours was closer to real time, and I think that was very important.
What we've been able to do is show people how important having that spatial lens on our information and on our analytics is. Walgreens is a 24-hour company. That means we need to be able to provide data on any device at any time, anywhere.
So many of the important decisions that we make within our company are based on location, where stores are going to be, how we want to merchandise those stores in terms of the items we want to have in those stores, and all of that is really driven by the wall map tool that we have.
WallMap allows us to provide spatial solutions to people that aren't experts in GIS. So we were able to deploy solutions that are much more user-friendly and easy to learn.
We made it broad-based, so all of our data is there and very easy to turn layers on and off, and to have some basic dashboarding so that anybody here at the company can consume Walgreens information in a map format.
Mergers and Acquisitions uses WallMap on a daily basis. Each of our managers are responsible for territories across the country, and they use WallMap to identify competitor locations. We look at distances, we look at population of certain Walgreens trade areas, we look at demographic information and how that could play into the business retention that we expect when we purchase pharmacies.
For our users that go out into the field, we needed WallMap Pro Mobile. And what that really does is allow people to use any sort of mobile device when they're out in the field so that they can look at data about our stores right there. Now we can actually have a tablet that follows us as you go, the map pans as you move, and I can go ahead and take inked notes against an aerial background, against a map background, against a market share background, against our stores, over the top of our competitors, right there out in the field.
What's amazing about the GIS platform is not just all the data that it can aggregate, but its ability to display that to make it easier for executives to understand what's going on and make the right strategic choice for the company.
At the core of how people behave is geography, and strategically having a geocentric approach and thinking locationally and geographically is huge. If you're not, you're missing something.
And now that we have had a lot of conversation about geocoding and geopositioning systems, we want to bring that back to a more focused application for creating maps in a data visualization system like Tableau. So when we create maps in Tableau, we need to create a particular what's called a geographic role. And what this is we have to define basically what are cities, what are counties, what are states, zip codes, that sort of thing. So we have to basically define what kind of map is it that we want to create with our data. So once we've defined that, so in this example, we've defined a state in our geographic role. We can then drag our data dimension of state onto our marks as we want to use it, onto our canvas, and then it will begin to locate the commonly recognized location, in this case of states, and you'll see that we've highlighted a center point for each of the states. And so here we basically just encoded a plotted point for each of these states with color encoding. Now we've taken our map one step further. We have taken the measure of profit from our measures. We've drugged that to color, and now we've color encoded each state based on its level of negative to positive profit. And so we'll see in our sort of reddish pink area there, the least amount or negative profit, and then our darkest green is the most amount of profit. Now we can choose different types of maps. Here we have a filled map, but we could also choose a circle map instead and go back to having our plotted points or center circles in the middle of each state. So again, this is dragging another measure. So in this case, we're going to drag sales or revenue to our marks here. And in this particular case, we're going to be dragging it to the size marks, and that will provide us with our plotted points with varying sizes for the amount of sales. Now in Tableau, we also have the capability of fine-tuning our marks. So if we drop down on either of these pills that we've done encoding for, either profit or sales, we can do some fine-tuning of transparency. We can edit our borders. If we want to give it a halo effect, we can do that. So as with all of these particular pills in Tableau, we can fine-tune any of the encodings as we deem appropriate. Now, we can also simply drag particular dimensions to the canvas if we wish. So in this particular data set, we have latitude and longitude. And you'll notice what we've done here is basically drug over longitude to columns and then latitude to rows. And that will then encode our particular plotted points to those geolocations. Now I may wish to create multiples in rows. So here I've highlighted that I want multiple mark types, so I've made that selection. You'll notice that we have basically two different maps defined here. We've got longitude in the columns, but in the rows I have two different maps of latitude. If I'd like, I can adjust the marks on one of those. So in this case, I'm going to keep one of those as an area map. In the other, I'm going to encode it or adjust the encoding to be a circle or a pie chart. And once I've done that, I can then select that I'd like this to be a dual axis map. And refreshing everyone's memory, that's a layering principle. So we're going to layer one of these maps on top of the other and then give an axis, a dual axis for our layered map, one on each side. So here we've layered, so we have the same column of longitude, but I have basically two latitude maps at work here. Now there are also a number of options that I can turn on for maps. So I can find these by selecting the map menu and going to map options. I can adjust the map style, so we see three different styles here. I can define what's known as a light map, so you'll see in very faint gray background the overall geographic map. My example in the center, or my style setting in the center, is a normal map, so you'll notice there it's a little bit better defined. My countries and geography is a little better defined here, and notice that I have oceans in this map. And then at the bottom, I have a particular style preference that I've selected called dark. So as you can see, this is just a different style preference, but it basically defines the same thing in a much darker style. The countries that are not highlighted or not encoded are basically blacked out, and then the ocean is seen as a very dark gray. So this is one of the style aspects or options that I can adjust with my map. I can also add a number of layers to my map, and so if we select map layers, you can see here that I can turn on or turn off coastlines, streets and highways, regions, states and province borders. So lots of different choices there of things I can turn on and off. So we've provided a whole list of layers for you here to choose. We could also add different default maps that come with Tableau. So here we could overlay a population map. So if I wanted to include my population map or households or any of these predefined maps, we could go ahead and add those as an option to our map. So here we're adding an option of demographics, so we could add population here. and now we see that population map overlaid. And notice that we have very high populations in California, Texas, Florida, and New York. Now, to summarize our lecture on spatio-temporal data visualization, basically maps in space and time. The three key ways that we can define this type of visualization are defined as what. Basically, we're focusing on objects, or where we're focusing on locations. That's the central interest. Or when. We're focusing on time. We want our audience to be looking at differences in time. Now, time could be points in time or time intervals, so remember that there are many different ways that we can express time. Yes, we can express it as a time and date stamp, but we could also express it as 10-minute intervals that we saw in the previous map, or 24-hour intervals. So lots of different ways we can express time. Remember that animation focuses on the change or trend of the data and events versus a side-by-side comparison. And remember that geocodes or geocoding is a series or a system of measurements of latitude and longitude, forming that grid of north, south, and east, west. This concludes our lecture on spatio-temporal visualization